like little children. I won't go into my, won't talk too much about my distaste for small children. One of the reasons why is, of course, they don't appreciate harmonic oscillators. So that's always a problem. Okay, so let's, I want to finish this up this week. I want to talk a little bit about this today, kind of left where we left off, recap our discussion about harmonic oscillators and vibrations. Starting to work through the homework where I've applied all of this to a chemical problem, which is in some sense measuring the length of a bond and ambiguities that arise from that concept of measuring a bond, the length of a bond. I hope you're getting some appreciation for some of these variables, behaviors, and we'll kind of look at them more carefully by today. So I want to, again, our central focusing idea is that we're treating bonds like just plain old springs. And the take-home point from that today, and forever, in some sense, in all chemistry, is that this gives us this beautifully equally spaced set of energy levels. Right? They're all spaced by this harmonic frequency. So you get these equally spaced levels, meaning that every transition, right, every absorption, if you will, between two different levels, 0 to 1, 1 to 2, or something like that, is all at the same frequency at omega. So you get this really, really simple energy level spectrum for a molecule. In this case, just like a regular, just a single spring, okay, just a diatomic molecule, something like HCl or N2. Starting tomorrow, we'll think about expanding this concept to something that has many bonds. Okay, because right now we've only talked about one spring, but what about something that has many springs? So we're going to see how the energy level structure works when you have multiple springs. We're going to find a special way to treat all of them independently in a special way. And we're basically going to recover this harmonic oscillator behavior even in big molecules. We're going to find that a molecule can be represented by some number of these collective springs, where all the springs are moving collectively in these special ways, where each one acts like an individual spring, its own spring. So we'll work that out next class. And I just want to just, bury this diatomic approximation into the ground because we're just going to come back to it over and over. The real thing, and this is what we're exploring in the homework and what you'll explore in the next rotation in lab, is the idea that in fact bonds are not harmonic, but they're anharmonic. We showed this potential called the Morse oscillator, which doesn't have a harmonic energy level structure. Right? It doesn't look like a parabola of potential energy, but rather it has this kind of funky thing that looks like a parabola down at the bottom, lowest energy for the bond, and it deviates away from quadratic behavior at two limits. And we identify chemically what those two limits are. One is that when you start to compress the bond and make it shorter, you're pressing against those electrons in each of the atoms want to press against each other, right? There's going to be this repulsive force. One, there's a repulsive force from the spring wanting to expand, but also you have the repulsion of the electrons in the atoms that increase significantly as the atoms get closer and closer together. We have a really, really, really sharp kind of short end of the potential. Very, very sharp. The energy increases rapidly as you start to compress. It gets harder and harder and harder to squeeze it together because the atoms will push apart. And then on the long end, as we stretch it, the idea is that the bond is getting weaker electronically, right? The connection between the electrons as we stretch the nuclei apart are weakening. Right, so the electronic character of the bond is weakening as we're stretching the atoms. The electrons are on average further apart. That weakens the strength of the bond, if you will. So since the strength of the bond is, the stiffness of the bond is a function of its distance. So as the atoms go farther and farther apart, the electrons interact less and less, the bond becomes less and less covalent. And so the bond doesn't resist nearly as hard as you would expect. Over the long end, it just rolls off eventually to the point where the atoms are now completely separated. They don't talk to each other anymore. There's no covalency between them. And therefore, it's not really a spring. It's two free atoms. So we get this kind of roll off here. So the idea is that locally around the minimum, right at low energy, say you're in a ground state, nothing's exciting happening, it looks very quadratic. If your V equals 0, the ground state, are very harmonic. Then as you start to get V higher for the higher energy levels, it becomes increasingly more and more anharmonic. And this is entirely general. Every bond in some sense looks like this. They don't all have the same behavior at long range or close range. They vary slightly, but by and large, the last 100 years of research on the potentials of these bonds, right? People go into experiment and measure these potentials experimentally. And when you do that, find they all roughly look like this. Some of the long range and close range behavior at the limits looks a little different. Some atoms interact with each other at longer range than other types of atoms. So it might not roll off as quickly, but in general, it has this behavior. Okay, so they all kind of look like this. Just at the limits, it starts to fail. But by failing, I mean it's just off a little bit. But so up to 99%, if you will, accuracy, this is a really, really good approximation for what a bond looks like. Take two atoms and pull them apart. It has this potential. This is a totally general way to approach the concept of a bond, strength of a bond. And if we can determine this spectroscopically, right, if we can figure out how anharmonic the system is, we can determine something about the strength of the bond, which is the distance from this point to this point, the dissociation energy. It tells us something about that bond strength. And you're going to look at this in very close detail in lab in the next couple of weeks. Empirically, what happens, right, we don't actually observe this potential, right? We can only derive it kind of indirectly through experiment. And the experiment that we always do to measure this is to measure the spacings between each of the levels. Right? And again, that's a really nice thing to do because if it's perfectly harmonic, every transition between two different levels, 0 to 1, 1 to 2, 2 to 3, and so on, all have the same frequency. They're all equally spaced. Right? So they would all show up at the same place in your spectrum. But in a Morse oscillator, the energy of the levels, again, is harmonic, equals 1/2, right? It looks just like this. But there's this small quadratic correction that you add to each level, right? And this correction gets bigger as V squared. So every time you go up a level, this extra term gets larger and larger and larger. For a given V, it's fairly small, right? X of V is about 1,000, generally 1,000 times smaller than omega. So in some sense, the harmonic oscillator is good to about 1 part in 1,000 for most molecules. So what the perturbations due to the fact that it's not harmonic appear at about 1,000 down, if you will, in sensitivity. And you can see that even in the ground state, right? V is 0, even in the ground state, there's some correction here, 1/4 times omega xe. So all the levels are affected. All the positions of all the levels are affected by the inharmonicity, but it's a small effect, right? And it gets bigger, right, as you go higher and higher up the ladder. And so you can kind of see this here. Here are the energies for each one of the levels. Right, the first level is at 1/2 omega minus 1/4 omega xe. And the next one's at 3/2, right? These are each separated by omega roughly, 1/2, 3/2, 5/2. But the difference between them is getting smaller, right? This difference is 9/4 minus 1/4 in the correction. That's 8/4, that's 2 times this. And here's 25 minus 9 over 4, that's 16/4. That's 4 omega xe, right? So it's getting the spacings are getting smaller as you go down, as you go up in energy. Right? So if we can measure what that would say is that on our spectrum, if we were to look for the 0 to 1 line, then the 1 to 2, then the 2 to 3, right? We're kind of sequentially exciting our molecule with light and looking for absorptions. In this situation, all of those get absorbed by the same frequency. We see one absorption because they're all at the same frequency. But here you would see a progression of absorptions that are decreasing in energy or frequency as V increases. Right? Because this spacing is larger than this one's larger than this one. So as you go up in energy, we see a series of lines in decreasing frequency associated with each sequential step up the ladder. Right, so by measuring, by being able to see where each of these little rungs of the ladder, the 1 to 2, the 2 to 3, the 3 to 4, the 4 to 5, and so on, where those show up in your energy level spectrum, in your spectrum, your infrared spectrum, tells you something about how anharmonic the system is. It gives you a value for XE, fit this data to XE and omega, doing a linear regression. That's what you're going to be doing in the lab in a couple weeks. And so you can determine these XE values and these omega values experimentally. Right? So these are the numbers, this XE and this omega, these are the numbers that we get from experiment. And this is what we call the spectroscopic constants. The values that come from the spectrum, and they describe the energy level structure. And what describes the energy level structure physically? Well, it's the shape of the potential. So by measuring XE and omega, in some sense, you're measuring the shape of this potential indirectly. It's the shape of the potential, how deep the potential is, how steep it is, how shallow, how floppy, how strong the bond is, determines these values, X of E and omega. So if you can measure them, you're somehow, in some sense, indirectly measuring how anharmonic this potential is. So let me show you an example of that. I'll just look at some really, really simple data. All right, we'll just look at HCl. All right, you guys are looking at this molecule. Oops, sorry. On the problem set, all right, and I'll just show you on NIST, you can actually pull up some useful information about these molecules. Let me go ahead and bring it over here real quick. So let me show you NIST webbook. On the NIST webbook, this will actually be really useful for your iodine lab. You can look up this data for the iodine lab later on. If I type in HCl here. And for diatomic molecules, there's this special link here on NIST, constants of diatomic molecules. On that, this was made. This was invented. This was a NIST compiled all of this data for diatomic molecules decades ago. It was compiled by Gerald Kurtzberg, who is, in some sense, the godfather of spectroscopy and one of our only Nobel Prize winners. But one of the earliest. He was a Canadian and wrote a series of excellent books. And so what this list is like, again, we haven't talked about all of these things yet. But HCl, again, has different excited states, right? You think about the electrons in the HCl bond, well, you can excite them individually. We'll talk about those electron excitements later in the semester. And each one of these excited electronic states have a different label. So think about the hydrogen atom, the 1s, the 2s, the 3s, the p's, the d's. You have all those. Well, every molecule has states like that as well, and we give them special labels. We'll be able to interpret these labels soon, a couple weeks. But I want to go to the bottom state, which is the ground state, which we call the X state. Right, so this is regular old HCl, nothing's been excited, just a normal old molecule. And here's the omega E and the omega E XE values for HCl. So this is the harmonic frequency, 2990.946. That probably rings the bell if you've worked on the homework. You've probably never seen that number. And this is the product of X sub E times omega E. See, it's 52, right? It's about 1,000 times smaller, like we expect. So in general, HCl is a very normal molecule. It doesn't have it's a very covalent bond. It's slightly anharmonic, right? This number is non-zero. X and E value is non-zero. That means there's some anharmonicity, but it's fairly small. Right? And there's some other numbers here that we can talk about later. But these numbers, in fact, give us everything that we need to know about the spectrum of this molecule. Okay, by using these numbers, I can calculate everything. But the two numbers I want are omega E and omega E XE, because I can do my energy level calculations using these numbers. These are in wave numbers, of course. And omega E XE is 52 point, I'm just going to round it. Oh, no, 8186. Right, and that just as a helpful calculation, just to show you the scale at which the system is harmonic, this means that X sub E, or the X constant, is 0.0176 wave numbers. Right, and if we calculate the fraction of omega XE over omega E, right, that's the size, the relative size of the two. Right, you can see that's a pretty big number. 5.6 times 10 to the minus 6. All right, so HCl is actually really harmonic, right? It's inharmonic term. The size of this, right? Remember, omega E is the energy of the spring as a harmonic oscillator. X sub E is the correction for anharmonicity. So the size of X sub E tells you a little bit about how anharmonic the system is compared to the omega E, right? And their X sub E is 5.6 ppm, right? Very small value. So this means that the system is not very inharmonic. It's very mildly inharmonic. So in general, when we talk about HCl, we very rarely talk about it as an anharmonic oscillator because it just doesn't matter that much. Right? It's a very small value. We can look at other molecules, for instance. We can look at I2 later, for instance. You'll see that these values are much bigger. I2 is in some sense a much floppier molecule. It's much less. The covalency between two iodine molecules is not particularly strong. And so its X sub E is much larger comparatively. Okay, and again, I can now with these two values, I can calculate the energies of any state that I want. Right? Remember, the energy of any state is omega E B plus 1/2 minus omega E XE B plus 1/2 squared. I like a little squick inside, right? So I have everything I want. This is just a plug and chug at this. And I just plug in a V, calculate the energy of that level using the spectroscopic values, right? Which are very precise, right? They're 6 or 7 significant digits. These are real significant digits. So what I'm going to do now is I'm just going to say, let's look at some predictions. Right? How does HCl's? So what we would want to do is we want to calculate where we would predict what frequencies, what wave numbers we would predict transitions to be at, right? Remember, transitions in spectroscopy are energy level differences, or absorptions corresponding to differences in energy levels. So we need to think about the difference in energy between V and V plus 1. Right? This would be like, for instance, taking a molecule in the ground state V equals 0 and exciting it 1 quantum V equals 1. That's an absorption. And it's not too hard to show with just a little bit of algebra that this is omega E minus 2 omega E XE V plus 1/2. Okay, and that's exactly what we would expect. If XE is 0, then the energy gap between two adjacent levels is omega E. It's a fixed number, right? It's constant. So what happens is the spacing between levels gets smaller, proportional to X sub E. Our anharmonic constant. And so if we start to look at some HCl data, this molecule has been done to depth, excuse me. And what we'll do is we'll write down the transition that we observe. So this is the V to V plus 1, right? The label for this thing that we observe in our spectrum. We're going to look at the harmonic oscillator prediction. And then we're going to look at the Morse oscillator prediction, right? That's using the values above on the top of the screen, the omega E and the XE. And then we'll look at the experimental value for the line. All right, so we'll do the first transition, right? The 0 to 1. This is the line that you see. If you took HCl as a gas, different question altogether. We'll talk about HCl and aqueous solution. That's a very different system. Talking about HCl, the molecule in the gas phase, which is just a normal covalent molecule. You can buy this in a tank, HCl gas, pure HCl gas. You can make a little gas cell and put it in the IR instrument upstairs, and you see a beautiful spectrum. And you'll find this line exactly where you would expect it to be, right? It will be at omega E, 299.4946, right? But it's going to be minus this correction times 1/2, right, at V equals 0. But this number is really, really, really small. So we can just neglect it. And in fact, experimentally, that's true. What we predict let me change this number, 2990. I'll just go write 2991. And the Morse oscillator predicts it to be at 2991. And experimentally, we see it at 2990.9. So gets it right perfect, right? This is what I mean. HCl is a very harmonic molecule, traditional sense, in the sense that at low energy, when you interrogate a molecule, this is very typical for you to interrogate a molecule, say in the lab, it's at room temperature. These are wave numbers, right? These are kind of around the wave numbers that you typically measure things in organic chemistry. Right? Remember, CH stretches are around 3,000. So this would pop up on the IR upstairs. You see this really big spectrum, really straightforward, and everything looks harmonic to you up to some limit. But I can also, we'll talk a little bit about why I can do this. I can also jump 2 quanta. What we call an overtone. I'll redefine these for you soon. But we can jump 2 quanta. You have 2 photon excitation. Or rather, 1 photon going 2 levels, jumping 2 levels. And so for the harmonic oscillator prediction, we would expect that this would just be 2x that. It'd be around 6,000. Because again, the energy level spacing between individual levels is omega. So if we're going 2 levels, that would be 2 omega. All right, so we would just expect it to be this number times 2. Which is 5982. And for the Morse oscillator, we would expect, sorry, I'm just doing this. This is 5/2. So we would actually expect this to be at, is that right? Yeah. Yeah, sorry. Okay, 5668.2. So as you can see, it's the anharmonicity is really starting to kick in a little bit. Right, we predicted to be at 5982, but in fact, the Morse oscillator, because now we're starting to include this term XB, predicts this to be quite a bit lower. And if you go look at experiment, right on. The Morse oscillator is in some sense picking up the appearances to this inharmonicity and the potential. And you can see exactly in the experiment. In the experiment, these don't show up exactly 2x, slightly less by about 10%, 5%. All right, and the Morse oscillator encapsulates that behavior perfectly. All right, let's just look at one more example, right? So now we're going to go to the next, we're going to go to the third level, right? So we would expect that to be at, we would expect this to be at 8972, 8973. And in fact, what we observe in the Morse oscillator is 8347.5. An experiment, we see 8347. Okay. Well, let's put these numbers together. Let's just kind of roughly look at what's going on here. First of all, the harmonic oscillator prediction is just getting worse and worse and worse every level we get. And that's not surprising because every time we go up a level, we're adding more anharmonicity. The system is becoming more anharmonic. This term right here is getting larger and larger, right? Which making our levels get closer and closer together. So in some sense, the harmonic oscillator approximation, its error is compounding. Sequentially, all the errors we have from the 0 and the 1 state are compounded into the 2, which are compounded into the 3 state. Now at that point, you're off by almost 10%. But by including this extra term, right, by now fitting our spectrum not to a line, but to a linear function of a quantum number v, we now have a slope instead of just a straight line. You can see now we've brought the error down to less than a wave number. Okay, it's still not perfect. In fact, the errors are getting worse, right? This one's about 0.1, this one's about 0.2, this is about 0.5 error. Right, so the anharmonic approximation is still just an approximation. It's not perfect. So if we went to the 0 to 4, we would see that the Morse oscillator is off by even more than experienced. Okay, so it's just an approximation. Just an approximation. Right, so how would we fix that? Of course, right, you can see now the harmonic oscillator approximation is totally worthless once you get past the first level. It's not totally worthless, so it gets you in the right place, but it's not quantitative. So the question, of course, is how do you do better? Right? How do I resolve this small discrepancy? Again, it's a tiny, tiny discrepancy. Depends on who you ask whether you think this is an error or not. Spectroscopists would say this is an error because what we see is an increasing deviation as a function of the quantum number. As the energy increases, this deviation from Morse to experiment is getting larger. Even though it's a good approximation, it's only good so far, in the sense that it's diverging very, very slowly away from the correct answer still. So we would want to do something to it. We would want to fix this so that we can fit this more accurately. How would we do that? Well, the answer the spectroscopists come up with, how do we make another correction of this? The thing that they do is really stupid. But it works. Remember what one of the discussions that we had about the Morse oscillator, again, you probably don't remember this, it was a week ago, is that in some sense the anharmonicity is turning on continuously. So when you're looking at levels that are close to the bottom, just like the v equals 0, the potential looks a lot like a parabola. And then you go to the next level, it doesn't really look like a parabola anymore, but you say, hey, I can fit it to a cubic function that looks like a cubic function. Right? And the reason why it looks like a cubic function, not a quadratic, is because, again, the curvature has changed. It doesn't quite grow as fast as you would expect. So you would fix that by adding an x to the third. Right? And then you keep going a little further and you realize that the x to the third, the cubic isn't working, so you add x to the fourth. And then the potential would look like x to the fourth with the sublimit, and then you have to add another term, and add another term, and add another term. Right? This is just Taylor series approximations. They only work for a certain radius around the center. So you have to keep adding terms as you go up in energy. So how would the energy levels change? Well, you just add, every time you add a new term to your potential, you add a new term to your energy calculation. So when we go to a cubic potential, we get this quadratic term. So maybe Xe. When we go to the next level, which would be the potential to the fourth power position, we're going to get a cubic term here. And so there's going to be an additional term that appears at high energy, which we call omega E YE, because it's after X, that scales as V plus 1 to the third power. And there might be one to the fourth power, one to the fifth power, right? Again, totally arbitrary. There's nothing really useful here that we're doing. But what we're doing is we're saying that this potential, the physical potential of the molecule, the bond, it does have this behavior. In the sense that it's locally really close at the bottom, looks like a quadratic, and then it kind of deviates from quadratic as energy goes up. And the energy function that would go along with that, which is this one, fits the data perfectly. Okay, so in some sense, we are encapsulating the real chemical behavior of the system by just including extra terms in the most obvious way possible. But that's exactly how the potential works. It's that simple. Potential in some sense looks like a quadratic function, and as you get further and further away from the bottom of it, it starts to look more like a cubic. When you get further and further away, it looks like a quartic, then a quintic, then a hexac, right? It just keeps getting less and less quadratic. So the energy just goes as the polynomial as well. And I'll just prove that to you. Go on this for HCl. Here's omega E YE. Right? Look how small it is compared to this. It's another factor of 100 smaller. This is almost right. This is almost a factor of 1,000. Another factor of 100 down to the cubic. All right. So if we wanted to correct for that small deficiency in the higher energy levels, we would just need to fit this number to our parameters, fit that parameter to our system, and we'd be able to fit all the lines. Okay. All right. So again, this is the thing about spectroscopy is we're not really measuring chemistry directly. We're measuring things that give us some physical insight about the potential or about the system itself. But what we're doing by measuring YE and XE and omega E is measuring this potential very indirectly, but it tells us something about the shape of the potential and how stiff or strong this bond is. I won't go too much more into detail into it because the iodine lab and lab, the third rotation, really starts to accentuate these things. We'll come back to some of these topics next class, or actually today as well. Any questions about this? Cool. Okay, so let's talk a little bit about, let's continue on our thing about spectroscopy. I want to talk about vibrational spectroscopy in general. And we've talked about the frequencies of these absorptions, these omegas, and we tell you something about where the line shows up in wave numbers. But what about the intensities? Always two dimensions to a spectrum, frequency and intensity, energy and intensity. We've got a sense of where things show up in energy. But what about the intensities? Let's think about that. Remember, spectroscopy is as I said, two-dimensional object. It's a two-dimensional problem. You should always think about intensities like we think about in frequencies. Okay. So I want to ask a very simple question. So any molecule, so consider a diatomic molecule. Right, AB, with mass mu, force constant K, and harmonic frequency omega. Okay. Doesn't matter what it is, just some molecule. Right? And what I want to do is I want to take this molecule. Right? So again, we have, let's just remember, we have some energy levels here, V equals 0, V equals 1, V equals 2. And I want to think about transitions between all of these levels, right? So let's say our system starts at V equals 0 and we excite to V equals 1. That's going to be at frequency omega. Maybe we excite it twice. So this is called, this would be at frequency 2 omega, and so on and so forth, right? And there may also be another transition between 1 to 2 as well at roughly omega. Just roughly omega. Remember, these are perfect harmonic oscillators and slightly angry. Right, so you can think, if I just have these three levels, there are in some sense 3 different transitions that I can have between these 3 states. Right? I can excite V equals 0 by 1 quanta, V equals 0 by 2 quanta, or I can take the V equals 1 and excite it 1 to 2. All right, let's assume that the system is slightly anharmonic. Right. So slightly anharmonic. Right. And what that means again is that, let me call this omega and omega prime, so that omega is not equal to omega prime. Right, they're going to be slightly different. This were perfectly harmonic, of course, they're the same, but because of the anharmonicity, the 1 and 2 levels are closer together than the 0 and 1. Those 2 omegas will be at slightly different frequencies. All right, so we would expect in this triplet of states that we would see 3 lines. Right, we would see. Well, let me just write them down. We expect 3 lines. Right, the first one is the V equals 0 to 1. We have a special name for this transition. It's what's called the fundamental. It's like that fundamental pluck, that note. It's our A440 for our molecule. Right, and this is at frequency. This is at roughly omega. And then we're going to have this V equals 1 to 2 transition. That's going to be at a slightly different frequency. This is what's called a hot band. And this is at approximately omega prime, which is close to omega, but a little different. All right, hot band is a fundamental where the lower state V is not equal to 0. Okay. So it's a 1 photon transition, but it comes from a hot band, what we call hot band, which is an excited state. So it's excited from an excited state. And then finally, there's the other transition, which is at roughly 2 omega, which is the V equals 0 to 2. This is what's called the first overtone, right, which is borrowed from acoustics. Right, and it's roughly at omega prime plus omega, which is approximately 2 omega. These are very common transitions when people talk of. There's basically one other type of transition which we can't do yet, called a combination band. We don't have things to combine them. But these are the 3 kind of prominent vibrational transitions, and you can get a fundamental, a hot band, and an overtone. You ever see these terms in vibrational spectroscopy, infrared spectroscopy? That's what it's mean. That overtone is something that jumps multiple levels. So now my question is that I want to pose, and my answer is, which one is the strongest? Which one is most intense? Do we see all of them? It's a good question. Right. So I want to ask this question. So the question I have is, which transitions are what we call bright or allowed and which are dark or forbidden, depending on who you talk to. All right, so the idea is that we're going to do an absorption spectrum or an emission spectrum, doesn't matter. And we're going to ask which lines, which transitions absorb most effectively. Which ones have the strongest absorptions? Do any of them, or does some of them not have any absorption at all? All right, so bright means that they absorb, dark means that they don't absorb, right? I think we've already talked about loud. All right, so we need to answer that question. All right, and it's actually a really simple argument. A little bit of calculus, a little bit of quantum mechanics. We can actually come up with a general rule for this to answer this question. All right, so what we need to think about, remember, let's go back to that conversation we had about exciting an atom and a particle in bonds. We talked about light. And we said, what I had said that is that the way that light interacts with a molecule, the first approximation is it interacts with its electric dipole. Right, so we're going to treat our molecule like a dipole. We have this molecule AB. And we're just going to assume it might be polar, it might be not polar. All right, but it's got some dipole moment in some direction. Mu. It's a dipole. Sorry, let me make that cleaner. So we have this dipole moment here. Right, and we're going to interact some light with it, right? Some light at h bar omega. Sorry. So I can't write. Right, and let's just say initially that the system is in a V equals 0 state. Right, what happens? We want to excite the molecule. We want to put it in some new state, new vibrational excited state where it's stretched and wiggling. Right, so we're going to shine some light to it. And we're hoping that when we shine light to it, that this thing stretches out a little bit. I'll just call it like that. That's a stretch. All right, we'll just say it's in some new state K, whatever K may be, where K is not equal to 0. And the bond is stretched a little bit. Okay, so the dipole moment may be different. Right? Dipole may change. Remember, dipole has something to do with how much the negative charge and the positive charge is separated from each other. So as you stretch the molecule, it may get larger or smaller depending on how the molecule is arranged. So if a dipole is proportional to the charge distribution, so we'll write like an E, this is the strength of the charge distribution. Times R, the displacement, right, between the two atoms. All right, so as you change R, stretch the molecule, the dipole is going to change. It may change, it may not, but it's going to probably do something. All right, so a vibration may induce a change in the dipole moment. Right, might get bigger, might get smaller, it just depends on how it's vibrating. Now, in the case of a diatomic molecule, there's only one way to stretch it. Just make it longer, make it shorter. Either you're going to make the dipole bigger because you make it far bigger, you're stretching it, or there's no dipole at all. A and B are the same, doesn't change. So we don't really have to worry about it getting smaller, though that can certainly happen with more complicated molecules. All right, so what we're going to do, instead of thinking of the dipole as a constant, just an object that always exists and is unchanging, we now have this property, the dipole moment, which is the thing that interacts with the light. It's changing as the system vibrates. So the dipole changes upon stretch. All right, so we can think about how to represent the dipole as it displaces from its original state. All right, so we have this new dipole moment. We'll call it U prime of R. All right, that's our dipole for our new molecule. All right. Well, let's think about how we're displacing it. So before we stretch it, right, if it's not being stretched, the system's at equilibrium. Okay, so whatever the system is at equilibrium, zero displacement, the dipole is going to have some value, which is the value of the dipole of the normal molecule on the left. Right, so there's going to be some natural value of the dipole. We'll call it U0. Right, this is the dipole moment of the ground state of the molecule. We call this the permanent dipole moment. All right, so for instance, HCl has a permanent dipole moment because there's electronegativity difference between H and Cl. It's got a dipole moment. But N2, for instance, has no dipole moment. B0 is 0 for N2. Right, or O2 or Cl2, right? This dipole cancels out. All right, so it's either going to be some positive value or some non-zero value, or it's going to be 0. Whether it's polar or non-polar. So what's going to happen? Well, I'm going to displace the bond by some distance, and the dipole is going to change by some amount. I don't know about how much amount, but I can probably measure it. But what I can do is just linearize it and say that the dipole changes as a function of displacement times the derivative of the dipole with respect to position. All right, so we can think the dipole is going to change by some amounts as I stretch. All right, if I stretch by some fixed amount, how much does the dipole change? You get some slope. You get some linear slopes. We get some linear per part of it. And then, of course, it might change to some higher order as well. It may have some curvature. I'll show you some examples in a second. And so if it displaces, it might displace R squared as well, proportional to the second derivative. Let me show you some examples of these curves, right? So what we want to do is, if we want to think about how the dipole changes as we stretch, we want to plot the dipole, the moment of the dipole moment, as a function of the bond length. That's all I'm doing here. And I'm looking at what that looks like. So let me show you two examples of that. I actually pulled some up today. But let me put my screen back on for you guys. Yeah, okay, great. So here are some examples of a dipole moment. So as a function of a bond length. So this molecule, this is its typical, this is, I think, HCN. Okay. And the HCN bond length is probably about right here. So this is probably about R sub E right here. Right, so the molecule in its ground state, this is, so y-axis is dipole moment and x-axis is bond length. Okay, so this tells us exactly how the dipole is changing as we stretch the CH bond. CH bond length. And so the molecule at ground state is like sitting right here. Right, you can see as you stretch the molecule, you compress the molecule, you make it shorter, or you make it stretcher longer, right? It just goes as a linear function. Okay, so in this system, it's basically linear. So what this says is that, right, that the dipole moment as a function of bond length is just some number k times x, and k here from the data is 1.07 debye per angstrom. Okay, so the idea is that every time you move by 1/10 of an angstrom, the dipole increases by about 0.1 Debye, which is about 10%. All right, so in this occasion, in the case of HCN, this is the CH stretch of HCN. We don't ever have to worry about the dipole changing as R squared, because when we start to stretch the molecule, we're just stretching it in this region right here, and it's basically linear there. Okay, so the dipole is just a linear function of the stretch. You can see that as we start to pull the molecule apart, though, and you start to get to the point where the H and the C are starting to disassociate, and they're starting to break apart, you can see this thing starts to turn over. Right? So up here, if the molecule is super excited and we were stretching it, it wouldn't, and say the molecule in some state was at this bond length. It wouldn't be fair to say that the dipole changes a line, because right here it kind of looks like a parabola, an upside down parabola. Right? So it has a very different dipole behavior as a function of the system, of the bond length. So I'll draw that here. Right, there's also this region here. Right here it looks like kx squared. Okay. We'll see what this leads to in just a second. Let me just show you one more example of a slightly different molecule. So many molecules have this behavior where you just say, hey, it's roughly linear. If you double the length of the bond, double the dipole. Very simple approximation. That's very typical, but not all molecules do that. I just want to show you another example from the literature. I know it's in here somewhere. Yeah, here it is. So here's a really interesting molecule, a very common molecule in the atmosphere. This is the hydroxyl radical OH. This is the OH hydroxyl radical dipole function. Right, and R sub E is this point right here. Right, and you can see now it's not very fair to, and this is bond length to dipole. You can see at this point it's not really fair to consider a line anymore. And if I were to draw a line, kind of works okay locally, but the system starts to bend. Right, as you start to stretch the system, it doesn't really increase linearly. It hits some peak, and then the dipole drops drastically. Which has to do with the fact that this is a radical that unpaired electrons characteristic is affecting the bond significantly. And so here, using kx, sorry, mu 0 plus some number kx, it's a bad approximation. Rather, you would want to fit it to a quadratic function instead. Right, something like that. Just making up letters, the better approximation. Okay, so it depends. So what this is getting to is that the dipole moment as a function as you stretch the molecule, the dipole moment changes, but it depends on the electronic structure of the molecule how it changes. Okay, so you're actually what we're going to see is very different behaviors for OH versus a CH bond in just a second. All right, so just keep that in mind. The dipole is some function, and sometimes it looks quadratic, sometimes it looks linear. It may look also weird other ways, but generally it looks like one of those. So what does that mean? Well, remember what we talked about when we asked what's the intensity of a line in the particle box, right? The probability that you take a system from one level and shine light at it and you end up in another level, right? Those are the intensities of the lines. So the intensity is equal to the probability that I go from V to some level K using light. Okay. And that is going to be equal to the integral from negative infinity to infinity of our lower state psi V times the dipole operator, function of x, times the wave function for the ground state or the final state, dx. Okay, this is the same integral we had for the particle in the box. This dipole operator specifies how strongly does this state, psi k, sorry, I have the lines, I have the numbers flipped, sorry, let me apologize. This needs to be a k and this needs to be a v. Right, the dipole operator tells you how strongly does the light interact with the original level, and it provides that connective tissue that brings you into the upper level, which is the case level here. All right, and so mu of x, we've already written down. It's just some number mu naught, which is just the permanent dipole moment, plus 1/2 some number, we'll call it, times the derivative of the dipole with respect to position, evaluated at the equilibrium times x. Sorry, I didn't mean to have the x, the 1/2 there. That goes to the next term. 1/2 times the second derivative with respect to x evaluated r sub e times x squared. All right, and I'm just going to relabel this to be mu naught plus kx plus 1/2. What's another number that I like in the letter? Kx plus jk, we'll call it L. I don't like L. M, N, O, P. Let's just stick to Q. Q, x squared. All right, Q and K are just numbers. Okay, so the intensity of this line is going to be equal to some harmonic oscillator wave function times this dipole operator times the initial state, dx. All right, I'm going to break this into, and this is an integral over the entire space of the bond, which is infinity minus infinity. And I'm going to break this down into 3 terms. So what I'm going to do is I'm going to distribute the integral and the outer wave function on each one of these terms. So we're going to have the integral of psi k mu naught psi v plus integral of psi k times kx plus psi v, and so on and so forth. So I'm going to split things up based on the thing in the middle. So the first term, I'll write it like this. The first term is psi v star, sorry, psi k, my apologies. That's the final state times mu naught times psi v dx plus integral from minus infinity to infinity of psi k times kx times psi v dx plus the integral minus infinity to infinity of psi k star 1/2 q x squared psi v dx. All right, so I'm just splitting this into 3 different integrals. We're just dealing with the linear part, the constant part, the linear part, and the quadratic part of the dipole. We're just separating them out. All right, and we're not even going to evaluate these, right? We're just going to use symmetry rules, and we'll be able to figure out whether any of these are 0 or non-zero. So let me go ahead and move this over. I need a little more space. Oops. That did not work. Let's try that again. So let's look at these terms individually. So we first have the constant, the permanent dipole term. All right, so that's the integral from negative infinity to infinity of psi k star, some number mu naught, psi v dx. Since mu naught is a number, right? It's just the permanent dipole moment. Just the number. We can bring it out of our integral. And we have an integral of just two wave functions, psi k and psi v dx. Right? These two, so this integral is an integral of two wave functions, two different harmonic oscillator wave functions that are just at different labels. Right? Well, this might be the ground state, this might be the excited state. It doesn't matter, we just take different combinations. When is this 0 or 1 or non-zero? The only time this is 0 is when v is equal to k because of normalization. So this answer, this only has two answers. So it's mu naught if v is equal to k and 0 otherwise. So what this means is that if this is a delta v equals 1 transition, meaning that if k is v plus 1, such as if k is equal to v plus 1, right? We're just exciting by one level. This does not contribute. The take-home point is that it does not matter if the molecule has a permanent dipole. All right, the idea is that the only time the permanent dipole matters is if you're interrogating a transition between the same vibrational level. And we haven't really come up to a situation where you could do that. But what this means basically is that you've done nothing. Right? So the only time this term contributes is when you've done nothing. Right? So we don't really care about it. We want to excite it. Okay, so what that means is that vibrational spectra have nothing to do with the dipole moment. Sorry, the absolute value, the permanent dipole moment of the molecule. What that means is that molecules that don't have a dipole moment have some potential to be seen using infrared spectroscopy. Right? So do not need to have a dipole moment. Let's look at the next term. The next term is much more interesting. All right, so the linear term looks like infinity and minus infinity psi k star kx psi v. K is just the number. It's the slope of that curve that we looked at. And so we're left with psi k star x term psi v dx. Okay, so this kind of looks like a position integral. You guys did for particle in the box, except now we have two different states. We've seen this integral before. We saw an integral just like this when we were talking about the intensities of the transitions in the particle in the box. We had this integral that looks like two different wave functions of two different states, the initial and the final, an x sandwiched between them. And the same arguments apply here. The argument is that if this is odd, all right, let me do it like this, right? So the only way for this to be non-zero is if x psi v has same symmetry as psi k. All right, what do I mean by that? Well, let's look. So if psi v is even and psi k is even, then psi v k x psi v is odd, right? Because psi k times psi v is even. Even times even is even, but you have an x now, that's an odd function. So you have even times odd times even, which is the same as even times odd, which is odd. All right, so if this is true, this integral is 0. Right? Because you're taking an integral from minus infinity to infinity of an odd function. an odd function dx, which is 0. Okay, so what situations do we get even? All right, well, the even functions in the harmonic oscillator are the v equals 0, the v equals 2, the even numbers, right? The ones that are even about exchange. So even functions, even harmonic oscillator wave functions are v equals 0, 2, 4, 6, blah, blah, blah. They're the even functions, the even quantum numbers. And so what this is telling me is that if I go from an even state to another even state, I don't get any intensity. All right, so this means that, for instance, delta V equals 2, 4, blah, 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 are forbidden. With harmonic oscillator. All right, you can't go from an even state to an even state. So the only possibility is if you go from even to odd. So if we go, say, psi v odd and psi k even, then psi k x psi v is even overall because you're multiplying two odd functions times an even function that's even times even. And therefore, therefore you have an integral of an even function which is not equal to 0. It has to be not equal to 0, and that means then therefore that delta v equals 1, 3, 5, and so on are allowed. All right, so we can put all of this together. But since a harmonic oscillator, the only things that it can do is change v by one quantum number, right? Or an odd amount. All right. Well, it's not too hard to show eventually that the delta v equals 3s, the delta v equals 5s, they're very, very weak. Right? They have very, very low intensity. That'd be a worthwhile question to ask one point, maybe in the future here. So what we generally say then is that the selection rules, right, the allowed rules for vibrational transition. So the result is for a harmonic oscillator, only delta V equals plus or minus 1 transitions are bright. Okay, so when we go back, let me just copy and paste it over. This first question that we asked about these three transitions, bring it back over to this page. All right, we go back to this question. We have these three unique transitions. Which ones are bright, which ones aren't? All right, well, we already know that the V0 to 2 has to be forbidden. Right, so this is forbidden. Right? But the other two are allowed. So these are good. Okay, because delta V is changing by 1. All right, so what we would expect to see, in fact, is we would see a line at 0 to 1. We may see a line at 1 to 2. It depends on the 1 to 2 line, depends again how anharmonic the system is. It might be at a slightly different frequency. And then when we go look at the overtone, it's not there. So that's what we predict. Okay, so very simple. Right? All it says is in the end is that a harmonic oscillator, right? And it's a really easy thing to remember. Harmonic oscillator spectrum is an equally spaced ladder And light only allows you to climb one rung at a time. Very simple. Amazing. Equally spaced levels. You can climb them up one at a time with a light pulse, photon. That's all you can do. Now, last 5 minutes. When I talk now is that when you go take a spectrum, the only thing you see is the fundamental. So let's go back to the HCl data. And let's scratch our heads a little bit. Way back here. I gave you experimental transitions. Well, for the fundamental, should be a very bright transition, let me tell you, very much is. Typically in PChem labs, we actually study this. I just don't like dealing with HCl, so we don't do it. These are overtones, right? 0 to 2. And this is going to be really neat, right? Delta D equals 3. Right, but I just said that for harmonic oscillators, this line is forbidden. But so how did I measure it? I have an experimental number for that. It should be completely absent from my spectrum. It should have no intensity. The harmonic oscillator has no probability to go from 0 to 2. Well, what assumption have I just made? I made an assumption that this is a harmonic oscillator. It's not. It's an anharmonic oscillator, a very, very slightly anharmonic oscillator. And because of that, because it's slightly anharmonic, these selection rules get broken a little bit. So because it's slightly anharmonic, well, it turns out there's 2 different sources of anharmonicity, but if you think about it, because the bond is not perfectly symmetric, if we go back to our potential, the potential is not, if you think about the energy right here, the potential is not symmetric on both sides. Right? It has less of a slope on this side than it does on this side. Right? So in some sense, the system actually prefers to be on the right side right here. Because there's more, this is less energy, more energetically favorable. There's less of a penalty to stretch the bond than there is to compress the bond. Right? So the system actually tends to exist somewhere in this vicinity, somewhere off R sub E. Right? The mean of the wave function somewhere over here. Slightly right biased, right? What does that mean? Well, that means that these functions are no longer even or odd. Remember, what even or odd means is that they're symmetric about x equals 0, right here down the middle of the potential. But if the potentials are slightly shifted off a little bit, where the peak of the potential, I'll just draw it, right? Looks something like this instead. Whereas harmonically, you would predict it to look like this. Right, something like this instead. Harmonically, you'd expect it to be right in the middle, but because of the anharmonicity, it prefers to be on the right a little bit. Well, this wave function is no longer even or odd anymore. It has no symmetry. We've broken that symmetry. Right? So, and all of the wave functions are going to be like that. Because again, the potential always prefers to be on this side than this side. There's just less penalty. So everything is kind of skewed off from the center of the potential a little bit. And therefore, none of the functions are even or odd. They're only approximately even or odd. They're just slightly shifted. And so when I do this even or odd calculation, it doesn't work anymore. There's no more symmetry anymore. So that means every combination of every wave function will likely lead to a non-zero value. The ones that lead to the largest value are the ones that are different by 1. Right? 0 to 1's interval is going to be large compared to 0 to 2. But because the functions aren't even or odd anymore, they're asymmetric, all the transitions will have non-zero intervals. They're all allowed. And so any molecule that's anharmonic, which is every molecule, has some intensity in their overtones. Right? It's just a matter of how anharmonic it is, that how strong the overtone. Right? So molecules that like HCl, for instance, HCl, you can see the overtones for HCl. I mean, I showed them pictures of them for you. We wrote down the numbers for them, the frequencies. They exist, but they're really, really weak. They're thousands and thousands of times weaker in intensity than the fundamentals. Right, so the intensities are really small because those wave functions are only slightly asymmetric. They're pretty much even and odd, but they're not quite. So the integrals don't go exactly to zero. And so then if you look at more kind of complicated molecules, for instance, let's see if I can find a good one for you. This is the last thing I want to show you guys. This is from that HCN study. And here are the intensities for the different overtones and the fundamentals for HCN, the HCH stretch and HCN. You can see here, so it predicts the intensity of 0 to 1 to be 54. The 0 to 2 is 1.5, right? It's about 25 times weaker. Right, so it's still appreciable, but as you can see, the integrals are not exactly completely zero. They're just a lot smaller. And as you start to drive up to higher energies, higher VLET levels, again, those wave functions are oscillating much more rapidly. They don't integrate that well, and you can see the intensities die off as orders of magnitude. The next one is 3 times weaker. This one's 10 times weaker, 10 times weaker, roughly 10 times, and so on and so forth, 70 times weaker. Okay, so this is what a real spectrum looks like. It's not just the 1 to 0 and 0 is everywhere else. What you do is you have a slight roll off from anharmonicity. This is entirely due to the fact that HCN is just slightly anharmonic. It's not perfectly harmonic. And this leads to these transitions to be slightly visible in your spectrum. But again, you have to have really, really strong lines to see these. Right? If the intensity of this were 100, then you would only see this at level 2. It's 50 times weaker. Okay, so you have to have a very sensitive instrument to detect these things. Okay, that's all I have for you today. What we'll start out next class is we'll come back to this concept where we're going to do polyatomic molecules instead. We're going to talk about very, very simple rules on how to take this diatomic information and to come up with a model for polyatomic molecules. All right, have a good one, guys. This is Lehman and Smith. This is the 90s. 1990?
How long?
This is the knowledge. These kind of information work. No one was able to do it. I overturned it.
I was hoping you were at least one person could accompany. Professor for that.